We present our work, Enhance Obstacle Avoidance for Reactive Mobile Manipulation using an Implicit Nodal Map. Recent developments in both perception and control have extended the capabilities of reactive controllers. Generating motions reactively allows more robust behaviors and faster total execution times. However, current approaches cannot perform inside clutter scenes due to how they model obstacles. On the other hand, running these controllers without information about the obstacles can lead to collisions as shown on the video. Our work focuses on extending these methods to consider collision avoidance in clutter scenes. Our approach considers a robot working in a confined space, such as a bookshelf, with the objective of reaching a desired target pose. In order to model the scene efficiently, we made usage of assigned distance field, or SDF, due to the capabilities of directly querying the distance of a point in space. In order to query the robot distance using an SDF, we represent the robot as a set of positions obtained by sampling points from its mesh. These point locations, alongside their distances and gradient information, are incorporated into the control problem, in which we consider first an inequality constraint using the robot point locations and distances, and second, an active collision cost that maximizes the robot total distance from the obstacles. And by using both components, our method is capable of producing collision-free motions. We first validate our approach in simulation. We design a reaching task with two environments to test our approach, resembling a clutter table and a bookshelf. We sample variations of both scenes by varying the height and location of different obstacles. In total, we tested our approach on 500 variations on each scene. We compare our approach against previous work that rely on geometry primitives. In addition to different level of precisions of the robot representation, such as spheres and different set of points. The result of our experiment first shown that running a controller without collision avoidance caused it to collide on 81% of the experiments. In contrast, by representing both the robot and the scene as collision primitives, performance improves. However, because the primitives representing the robot do not fully cover it, the robot still collides. Our approach of representing the robot as either spheres or points and using an SDF to model the obstacles achieve collision-free motions. Finally, by adding our proposed active collision cost, the performance improves across all variations of our method, achieving a higher performance of 88.5% by using the most accurate robot representation, considering 9,476 points. In addition, we perform an ablation regarding our active collision cost component. In this experiment, we sample an extra 100 variations for both scenes and check the performance by varying the gain of the active collision cost. We first consider a baseline of running the controller only using our inequality constraints. By running the controller only using the active collision cost, the system performs poorly. Our approach combines both components and achieves the highest performance. We tested our approach in a real-world platform. In order to model the scenes as SDFs, we manually collect 30 posed depth images for each scene and then use ISDF to reconstruct them. Our experiments consisted of a reaching task on which the robot needed to reach different predefined target poses. Each run ends with the robot collides, a timeout when the robot gets stuck, and a success when the robot managed to reach the target pose with a margin of 2 centimeters. Our first result shows that running the controller without any collision avoidance component fails in 70% of our experiment. This is due to collisions on the arm or on the robot base. In contrast, by modeling the collision as inequality constraints, we achieve collision-free motions. However, the controller gets stuck on local minima in 15% of the experiments. Finally, our approach, combining the inequality constraints and the active collision costs, achieves collision-free motions. And a success rate of 96% in our benchmark. Thanks for listening.